Hello everyone. So in next lectures we'll be discussing about graph data structures. So in this lecture I'll be introducing the graph data structure, its terminology, and then we'll be talking about different representations of graphs, etc. In the next lecture we'll discuss about graph traversals like breadth first search and depth first search. A graph is defined as a collection of vertices and edges, collection of nodes, and interconnecting these nodes you will be getting edges. Mathematically, a graph is defined as G equal to V comma E. V represents the set of vertices and E is the set of edges. Next, we look at different terminology related to graphs. First, we'll take directed graph. If the edges of a graph is having directions, then we call it a directed graph or a digraph. Corresponding to a node, you can differentiate an edge as an incoming edge or an outgoing edge. For example, in this case, this edge is an outgoing edge for vertex 1 and an incoming edge for vertex 2. So correspondingly, we can have in degree and out degree of a vertex. The number of edges that is incoming to a vertex is called the in degree of a vertex. For example, node 2 in degree is 1, and out degree is the edges that is going out of this vertex 2, that is also 1. In this case, the in degree is 2 and out degree is 1. Self loop is an edge which is an incoming edge as well as an outgoing edge for a particular vertex. For example, this edge, which is an incoming and an outgoing edge for vertex 1, or which is an edge from 1 to 1, vertex 1 to vertex 1, is called a self loop. Parallel edges are those edges which are between a pair of vertices. For example, this edge and this edge are called parallel edges. An edge that is going from 3 to 4 and going from 4 to 3 are known as parallel edges. If two vertices are connected by an edge, then those vertices are called adjacent vertices. For example, 2 and 3 are adjacent, 2 and 4 are not adjacent vertices, 2 and 1 are adjacent vertices, etc. So if two vertices are connected by an edge, then we call it adjacent vertices. A digraph is known as a simple digraph if there are no self loop and parallel edges. In the previous example, this was not a simple digraph, but here this is a simple digraph. There is no self loop and there is no parallel edges. In that case, this graph is known as a simple graph or a simple digraph. If the edges of a graph is not having directions, as we have seen in the previous example, then we will say it's an undirected graph. Or by default, if you say graph, it represents undirected graph. In the case of an undirected graph, we talk about degree of a vertex instead of in degree and out degree. Vertex 1, the degree of a vertex 1 is 3, degree of the vertex is 2. There is no in degree and out degree. This edge is treated as incoming as well as outgoing for this vertex, incoming as well as outgoing for the other vertex. So if there is an edge from 1 to 2, it will be counted in both ways, for 1 and for vertex 1 and vertex 2. So here in the case of undirected graph, we will be discussing about degree of a vertex, not in degree and out degree. Look at this example. This graph has 7 vertices, 1, 2, 3, 4, 5, 6, and 7. Here we can see that there are two components to this graph. 1, 2, 3, 4 as a first component, 5, 6, 7 as the other component. If there are more than one component to a graph, then it is called a non-connected graph. If all the components are, or if there is only one component for a graph, then we say it is a connected graph. This is a non-connected graph. For example, if there was an edge between 4 and 6 like this, then this would have been a connected graph. Let's say we had an edge between 4 and 6, and this was a connected graph. And if we say something like, if you're removing this vertex, if you're removing a vertex from this graph, for example, if you're removing a vertex 4 from this graph, in that case, then this edge will be removed, this edge will be removed, and 4 to 6, that edge also will be removed. Then the graph will be divided into two connected components, or now the graph is non-connected. Such vertices are known as articulation points. For example, if you had 4 to 6 and 2 to 5, two edges, and then if you remove this vertex 4, still the graph is connected. So at that point of time, we will not say 4 as an articulation point. So if the removal of a vertex makes the graph to be non-connected, then those vertices are known as articulation points. So this is an example of a connected graph. Strongly connected graphs. In a strongly connected graph, starting from any vertex, you can reach any other vertex. There is a bond between every pair of vertices, or you can say there is a path between every pair of vertices. From 1 to 2, there is a path. 1 to 3, there is a path. 1, 2, 5, 4, and 3, there is a path. 1 to 5, there is a path. 1, 2, 5. So this graph is known as strongly connected, and this terminology is used only in the case of directed graphs. If the directed graph is satisfying the property that there is a path between every pair of vertices, then we say it is a strongly connected graph. In case of undirected graph, we simply say it is a connected graph, not a strongly connected graph. So, for example, if this edge was in the reverse direction, 4 to 5, then there is no path between 1 to 4, so it is not a strongly connected graph. So, the list of edges or the sequence of edges from a vertex to another vertex is known as a path, and a path starting from a particular vertex and it is reaching back to the same vertex is known as a cycle. For example, 1, 2, 5, 4, 3, and 1. It's a cycle. It's a path as well as a cycle. So the sequence of edges from one vertex to another vertex is known as a path, and a sequence of edges from one vertex to the same vertex is known as a cycle. Directed acyclic graph. These are directed graphs with no cycles. This was not a directed acyclic graph, but this is a directed acyclic graph. There is no cycles. If you start from any vertex, you cannot reach back the same vertex by traversing through the edges, or you cannot find a path from a particular vertex to the same vertex. So that sort of a directed graph is known as a directed acyclic graph. That has got a lot of applications in graph theory. Topological ordering in a directed acyclic graph, this is a property or it is possible only in the case of directed acyclic graphs. In a DAG, we can arrange the vertices linearly in a single line. For example, consider this directed acyclic graph. You can see that this can be arranged in a linear scale or a linearly in a single line such that there are no edges going backwards. All the edges will be going forward. 1 to 3 there is an edge, 1 to 2 there is an edge, then 3 to 4. So this sort of arrangement is known as topological ordering, and topological ordering is only possible in the case of directed acyclic graph. For example, if you had a cycle, then there should be an edge going back in the backward direction. So In a topological ordering, you can say that there is only edges in the forward direction and the vertices are arranged linearly in a single line. Next, we look at representation of graphs. For representing a graph, we need to represent two things, the set of edges and the set of vertices. We will be looking at three different representations: adjacency matrix, adjacency list, and compact list representation. First, we'll look at adjacency matrix representation. Consider this undirected graph with 5 vertices, g equal to v comma a, n equal to 5, and number of edges equal to 7. 1 to 2 there is an edge, 1 to 3 there is an edge, 1 to 4 there is an edge, and so on. Number of edges is equal to 7. So the adjacency matrix representation is this: for any vertices I and j, if there is an edge, then we should mark 1 inside the matrix. So we'll be taking a matrix of n into n, where n is the number of vertices, in this case 5 by 5 matrix, and for I comma j, a of I comma j equal to 1 if there is an edge. For example, 1 to 2 there is an edge, so you'll mark it as 1 here. 1 to 3 there is an edge, so 1 3 is marked as an edge 1. 1 4 there is an edge, so we'll mark it as 1. 1 5 there is no direct edges, so we'll mark it as 0. So this is the first row in the adjacency matrix representation. Second row corresponds to the second vertex. 2 to 1 there is an edge, 2 to 2 there is no edge, 2 to 3 there is an edge, 2 to 4 there is no edge, 2 to 5 and there is no edge. So this is how we represent adjacency matrix. We take an n into n matrix and we mark corresponding column I comma j equal to 1 if there is an edge between that I vertex to j vertex. This is the third row which corresponds to the vertex 3. 3 is vertex 3 is linked to 2, 1, 4 and 5. So only 3 by 3, 3, a of 3, 3 will be 0, all other will be 1. So this is corresponding to the fourth vertex and this is corresponding to the fifth vertex. So this is how we represent the adjacency matrix. So the corresponding graph is represented as a matrix, and inside the matrix, if there is an edge between vertex I and j, then correspondingly in the matrix a of I comma j is represented as 1, otherwise 0. In this matrix, you can see that the diagonal elements are zeros, means that there are no self loops in the graph. If there is a self loop, then only these entries will be 1, otherwise it will be 0. So the diagonal entries corresponds to a of 1 1, a of 2 2, a of 3 3, a of 4 4, a of 5 5. So it represents the edge between 1 to 1, edge between 2 to 2, etc. The second representation is adjacency list representation. Here we take another graph with vertices 10, 20, 30 and 40. 10 is connected to 20, 10 is connected to 40 and so on. So here we represent the graph as a list of or an array of singly linked list. Corresponding to each of the vertex, we will create a header node. 10 will be having a header node, 20, 30 and 40. So it's an array of singly linked list. Corresponding to vertex 10, you will have a linked list. 20, there is another singly linked list. 30, another singly linked list. For vertex 40 also there is one more singly linked list. So the first edge from 10 to 20 is represented as a node in the singly linked list. So the data item will be 20 and the link from there will be marked with the next node that is connected from 10, that is 40. So it will be having a node 20 and a 40. Here the link will be pointing to null. Vertex 20 is connected to 10, 30 and 40, and here it is pointing to null. Vertex 30 is connected to two vertices, so it is connected to 20 and 40. So corresponding to each edge, you will be creating a node in the singly linked list. Next, we'll do some analysis on adjacency matrix and adjacency list representations. In the case of adjacency matrix representation, for accessing an edge, we may have to access all the elements in the matrix. For example, you would like to find out an edge between two vertices, then we'll have to access or we'll have to pass through. If you want to access the edges, we'll have to pass through all the vertices, sorry, all the entries in the matrix. Means that this matrix has n into n number of elements. So the time taken by any algorithm accessing the edges in a graph, which is represented in adjacency matrix representation, is going to be order of n square. Whereas to access an edge in the case of an adjacency list representation, we'll have to pass through each of the list. That is, there are 4 lists in this case. That is number of vertices plus each list contains elements corresponding to the number of edges. Edges that too twice means that for each edge you will be marking it as 2 nodes, one for along one in one singly linked list and the other will be in the another singly linked list. For example, this 20 is marked in the this edge is marked with this 20 and this the same edge is marked with the 10 here. So total time taken will be order of number of vertices plus 2 into number of edges. So it is order of n plus 2e. So you can see that the analysis on the adjacency matrix and adjacency list representation, any algorithm which access the edges in the case of adjacency matrix representation is going to be order of n square, whereas the adjacency list representation it will be order of n plus 2e. Next, we will look at something known as cost as adjacency matrix, which is very similar to adjacency matrix, where we have weights associated with edges. So correspondingly, for example, the edge from 1 to 2, there is the weight is 9. Edge from 1 to 3, there is the weight is 4, and so on. So instead of marking 1 in the case of adjacency matrix, we will mark the cost in the adjacency matrix. That's it. That's what we call it, cost adjacency matrix. So instead of and if there is no edge, then we'll mark it as 0 or any other entry, which can be infinity or minus infinity, whatever. That depends upon your algorithm or the program which you are writing. But the edges will be represented by using its weights or the cost associated with that edge. That's what I mean by cost adjacency matrix. Next, we look at compact list representation. Compact list representation is another representation of a graph, which is using simple arrays for representing the graph instead of linked list and dynamic allocations and all. But the total time taken or total space required for storing the graph will be less, or it will not be that much compared to the adjacency matrix representation. For example, let's take the same graph with 5 vertices and 7 edges. Then the total space taken in the graph, in the array for representing this graph will be number of vertices plus 2 into number of edges plus 1, that is 21 values. So the time taken for accessing all each of the elements also will be related to order of v plus 2e. So this is how the compact list representation looks like. Compact list, in the compact list representation, the first entry will keep it as blank, and the first few entries, that is 1 2 3 4 5, there are 5 vertices, and these 5 entries will mark it as we'll use it for representing the vertices. And after that, one entry or one place in the array will keep it for something else. We'll see that. Then the next entry onwards, that is so total, the initial value will keep it as not used, and uh, entry is equal to the number of vertices plus 1, that is 6 boxes will keep it pending. Then here we'll mark the first edge, that is 1 to 2. So the edges from 1 to 2 will mark 2 here. Then there is an edge from 1 to 3, will mark it 3 here. There is an edge from 1 to 4, we'll mark it here. So first vertex is over. Then the next, we'll take the next vertex, vertex 2. Vertex 2 is having an edge from 2 to 1 and 2 to 3. So 2 to 1 and 2 to 3. So we'll keep on adding like this. Well, adding like this for vertex 3, there is an edge from 1 to 3 to 1, 3 to 2, 3 to 4, and 3 to 5. So it is 1, 2, 3, 1, 2, 3, and 4. So this should be 5. Sorry, this should be 5. So like that we'll mark. Then we need to fill up these places, so that we need to differentiate which are the positions in the array which corresponds to the first vertex, which are the positions which corresponds to the second vertex, and so on. We'll mark it like this. So the vertex, so the edges of the first vertex is starting at location 7. So at location 7, you can see the edges from the second vertex edges are starting at location 10. The third vertex edges are starting at location 12. Fourth vertex are starting at 16. Fifth vertex are starting at 18. Sorry, 19. It has got edges 2, 3, and 4. So these are the edges 3 and 4. Now we need to fill up these two places, not used places. So this place is marked as the next entry, that is 21. Now we can say what are the number of edges, how many edges are there from vertex 1. Vertex 1 has got 10 minus 7 number of edges. Vertex 2 has got 12 minus 10 number of edges. Vertex 3 has got 16 minus 12 number of edges. Vertex 4, 19 minus 16. Vertex 5, 21 minus 19 number of edges. And the number of edges, sorry, the edges are available in edges of one vertex 1 are available at 7, 8, and 9, just before this value 10. Vertex 2's edges are available at 10 and 11 positions, and so on. So that is compact list representation. So we have seen three different representations of a graph: adjacency matrix representation, adjacency list representation, and compact list representation. The same thing in the case of directed graphs, adjacency matrix representation of directed graph, there is no difference at all. In this case, for an edge, we will be considering the direction as well. 1 to 2, there is an edge, whereas 2 to 1, there is no edge. So this represents only in one direction. So that's how we represent in the case of adjacency matrix in the case of directed graph. In the case of adjacency list also, in the adjacency list of directed graphs also will represent it like this. Using the same technique, we'll be having an array of linked list corresponding to each of the vertex. Corresponding to the vertex 1, this is the list. Corresponding to the vertex 2, this is the list. And at the end of the list, it will be pointing to null, and so on. So that's all about graphs and representation of graphs. Thank you.